Alright, so besides the selection as well as projection operators we showed before, some other operators can also be implemented with this one-parse algorithms. In this page, we show you with another example for the operator, the elimination of duplicates operator. It can be denoted by the delta R, right? The delta denotes the duplicate elimination operator. This R denotes one relation. So based on this operator, we can remove these duplicates from the relation, right? It can be very useful for some operator like the set operator, the union, as well as the join, as well as some other set operators for among the relations. So to eliminate the duplicates from a relation, we may have to keep a record or keep a dictionary in the memory in order to maintain one copy of every tuple we have seen before, right? So we can check, for the other tuples, we can check if we have seen this before or not. So to keep this dictionary in the memory, we can use different data structures actually. So we can either use this balanced search tree, right, or we can use the hash tables instead. It really depends on the data structure we use for maintaining this dictionary in the memory. So also depends on the number of tuples we have in the data structures. We may have to, different time costs for maintaining this dictionary. For example, if we plan to use this balanced search tree to maintain such a dictionary, to keep records of all the copies of the tuples we have seen before, if we have like n tuples to be stored, then the time cost for searching inside this tree will be about big O n log n, right? However, if we are maintaining this hash table for the dictionary, then the cost will be about big O n instead. It really depends on the data structure we are using here for maintaining this dictionary. It can be either big O n log n or can be a big O n instead. So this is the time cost for maintaining such a dictionary in the memory for the elimination duplicates of this operator, right? Besides this, we also have some requirements for the memory space actually for implementing the algorithm for the operator. So first of all, we may need to have one buffer to store the one block of the input tuples, right? It is required. We may need to use m-1 buffers to store one copy of each distinct tuples in the relation. If you still remember m, right, this m denotes the number of blocks we can store in the memory, we showed before, right? And also depends on the relation or the table. If this R is actually, clustered, then the space cost will be about BR, right? On the other hand, if this R is actually unclustered, we may have to search for all the tuples, go over all the tuples to access the tuple records, right, to check if it is duplicated or not. And if it is unclustered, the cost will be about TR instead, the number of tuples in the relation. Here we also have one assumption or one requirement. Normally we assume that it's B delta R. It denotes the number of blocks for storing the distinct tuples in the relation. This B delta R is no greater than m. In other words, it is enough for us to store all the distinct tuples in the relation. We store one tuple in one block, and the number of blocks we use for storing all of these distinct tuples in the relation R is no larger than the size of blocks we can store in the memory. This is one requirement or one assumption for implementing this operator with a one-parse algorithm. Okay, so this is another example. Besides this, we can also have some other operators like the grouping as well as binary operators we show later.